BC Final project. In this project we are going to be discussing real-world applications of calculus, because there's always the age-old question of, am I ever going to use this again? Well, depending on your career, you very well may. So the first concept we're going to talk about today is volumes by revolution, which is very helpful in calculus as you can use it to find the volume of non-traditional looking graphs and shapes. So things with some kind of curvature, with multiple curves, with oscillation, we can find in a certain boundary what the volume of that space would be when it was rotated around an axis of revolution, which is great for math. But it's also really good in the real world because you can use this same concept to measure the volume of objects that are harder to measure with traditional tools, such as very large buildings or vases with unconventional curvatures, and even things such as planets out in outer space, because you can't quite get out there and take a measuring tape to them, now can you? So one example of this in the real world would be the Eiffel Tower. The Eiffel Tower's got a nice conical shape to it, and an equation that would represent that well would be e to the negative x. Now if you were to rotate this about the x-axis, you would return a shape that looks very much like the Eiffel Tower if you were to flip it on its side. So rotated around, you're going to find out your boundaries, which in this case you will not have any kind of negative bound because you're starting at the ground. And it's going to be the height of the Eiffel Tower. Bonus points if you know what that is. So your A to B would be 0 to the top of the tower, and then it's going to be pi r squared. We're going to pull the pi out because you're not integrating pi, you're integrating in terms of the radius here, which in this case is e to the negative x. So you're going to plug e to the negative x in for r and integrate from there, and that is how you would go about solving this equation and taking your volume here. In your careers, people such as architects would use this quite often because while straight lines and sharp angles are the most mathematically ideal structures to have, more often than not you're going to find some kind of curvature or domed lid or something on top of a building, curves to the walls, curves to the corners, and any kind of curvature is going to be much harder to figure out the space in the room if you don't have this method to use here. So you can definitely use that to figure out, how much space you're taking up with these different curves. Another concept we're going to apply to the real world here is vectors, specifically position, velocity, and acceleration vectors. The way we do them in calculus does seem a little bit impractical as far as the way some people would use them, such as a baseball player. They're not going to sit down out in the field and pull out a pen and paper and start doing a velocity vector. But in their mind, they're seeing a direction, they're seeing a distance, and they are meeting it there. So they're using vectors whether it seems like it or not. Some industries that do use it in a more traditional way would be like automobile makers or aeronautic industries, where they're being used to determine the speed and location of a vehicle, or maybe to find out where a satellite's going to travel or how far a rocket can go out in space. So one example here would be air travel coordinators, the people that deal with airplanes and air traffic. They communicate with pilots when pilots are coming near a landing site, and they're going to let them know how far they need to go and what direction they need to go in. And that is the definition of velocity, because a velocity has a direction and a distance, or a magnitude is what we're more familiar with. So from there, they can take the velocity vector, which we see here, as the v of x equals x prime y prime, and they can either back up and find out the position of the plane by integrating that same vector and plugging in the points, or they can find out where or how fast that plane may be moving based on where they started and how far they went in a certain time. And finding out the position, they would use what direction they're moving in and how far they're going to figure out where the original position or maybe where their current position is. If a plane were to get lost out somewhere, they could say we've been heading east at this speed, or we've been heading east for X amount of miles, and that's going to give them some way to find the position or some way to find their velocity or their acceleration, depending on what information they're given in the circumstance. So in careers, again, air traffic controllers, NASA, and automobile manufacturers all have regular applications of vectors in their work. They model, or they use it to model situations and make predictions without having to physically send out equipment and use resources and possibly waste materials, because they're out doing testing that they didn't necessarily have to do as far as figuring out the best way to do something. They may use it still to confirm their findings with math, but as far as getting to those findings, they're not going to waste materials. They're going to go ahead and use math and say this is what's going to work and this is what's not going to work. So it's very useful as far as being fiscally responsible and also just generally conscious of how much time and materials we're wasting in different situations. And I do believe that is the end of our PowerPoint here, and this video will end up on this slide that we are viewing right now. Thank you for your time. I hope you've enjoyed teaching this class as much as I've enjoyed being in it.